Okay, off we go. Welcome back. Let's see here. We are starting with section 1.7 today. Real quick before I forget. So I was going to give you all a quick reminder. Last time I sent y'all an email about this. But I think the system is, I hope, well understood at this point. But don't forget, homework number 2 got fully defined and assigned yesterday, right? If you look at the class schedule, right, homework 2 is now unambiguously set, right? So notice it's due on Sunday. And just a quick reminder, don't forget to do page associations for your submissions. This is very important. It is part of a complete submission. It is required. The grader is real touchy about this, and you have to do it or you will not get credit for your work, right? If you don't do page associations, you did not submit, right? So make sure to get those page associations done. And then let's see here. Was there another thing? I guess that's yes, and attendance. Right, so we're going to start doing attendance quizzes very soon. The holdup at this point is no longer the class roster. I think by the end of today, the class roster should be fully settled. The holdup at this point is that I have to get set up for this kind of thing. Right, so I have to create the Canvas site and the attendance procedures and all of this stuff. So just a reminder, there are again, a lot of procedures, right, concerning how we're going to do these attendance checks. They are all through Canvas. You have to do it through Canvas. You can't come up to me after class and say, oh, by the way, I was here, right? So it has to go through Canvas. That's what it is. So make sure to read. Hopefully you've already read it. Make sure to reread all of the attendance procedures that I have on the class website. It's in the, I think it's in the classroom rules section of the website, and make sure that you're up to speed on all that stuff. And I'll send out an announcement whenever I am set up and ready to go. I'll send out an announcement. Hopefully, also maybe making another announcement in class, and make sure everybody's appropriately informed. Okay, let's dive back in. So here we are, section 1.7. Coordinate systems are a tool that we use to do math. Right? There is an easily forgotten point here, and that is that they are arbitrary. Right? We tend to think of the plane as being, in fact, the XY plane. That X and Y is set up as so, or that is part of what that is. It's not true. Right? It's just a plane. Right? And we set up an axis system because it's convenient, because it suits our purposes, and I'm all for it. Right? But it is an arbitrary choice of, to serve our purposes, right? That we choose to define X and Y in a certain way. And again, big fan, rectangular coordinates, and we call them rectangular coordinates because of this picture defining, what they mean, where they come from. And you can see the rectangle, that's the name, right? And it has some nice features. Rectangular coordinates are unique. You give me any point in the plane, there is exactly one set of XY coordinates to describe that given point. Okay. It's easily taken for granted, but worth recognizing. It's also algebraically convenient, and I'm sure y'all have seen this in a linear algebra class. The coordinates for a point, when you're using rectangular coordinates, the coordinates for a point are the coefficients in how you write that as a linear combination of standard basis vectors. In fact, in a linear algebra class, this is the definition of coordinates, right? Flashbacks to Math219 or 221, whatever. This is kind of a special case of this sort of more general fact that when you take a linear combination of vectors, you're taking the same linear combinations of the coordinates. These are all fabulous facts. I'm all for all of these, but sadly, these are all peculiarities of the rectangular coordinate system. None of what we just talked about is going to hold for these other coordinate systems that we're going to discuss. Right? So heads up, right? And you got to be real careful. Don't go around taking these old assumptions that we've gotten really comfortable with, right? Don't go around taking these for granted because they're just not true. for these other coordinate systems. Okay, all right, so polar coordinates. I think a lot of y'all have probably seen polar coordinates before. You don't have to have seen them before. There's different ways to think about them. I don't know, maybe the sort of the first way a lot of people like to think about polar coordinates is that the polar coordinate called theta tells you in some sense by what angle counterclockwise from the positive part of the x-axis do you rotate to get to a particular direction. And then the coordinate r, I'm going to say in some sense how far you go. Well, let me try to hit it. How far you go in that direction. And you'll notice that I have how far in air quotes. Well, quotes. There. And this is another one of these annoying little awkwardnesses. You got to watch out for inadvertently, accidentally assuming something has to be positive when it doesn't. Right? How far suggests the distance. Distances are intrinsically positive. There is no such thing as a negative distance. There absolutely is such a thing as a negative value of r. And look, one way to kind of get accustomed to this idea is think of theta as defining sort of an r axis, if you will. And so, like, there's 0, and there's 1, and there's 2, and there's 3. Well, axes extend the other way as well. So there's -1, and -2, and -3. Right? So a negative r coordinate just means go the other direction. Is that cool? Yes?
What's the GP about the power?
Oh, yeah, I haven't gotten to that yet. Yeah, give me a minute. Yep. So this is a good way to think about it, and everyone should have some intuition for thinking about polar coordinates in this kind of geometrically convenient kind of sense. So your question is the very next thing to get to, and that is, we are eventually going to find it extremely convenient. I think that undersells it. Very useful, really nice choice to view this in a different way, and that is to think of there being a function. So I use the letter G just because I think F is, been overused. Right? So it's just a function, right? P, the subscript, means polar coordinates, right? So we're going to see functions like this for other coordinate systems very soon. But the idea is that this is a function that says if you give me two numbers, r and theta, we can take those values, r and theta, we can plug them in to this function, and out will come an x and a y, which we can plot there. Right? So instead of thinking of r and theta as sort of oddly defined, weird things that you see over here, no, they're just coordinates of another. You can think of it as kind of a rectangular coordinate system over here, the r theta plane. Okay. So the big question then becomes, well, how does this function work? How do you determine x and y from r and theta? And that's a pretty straightforward calculation. I'm going to suggest, let's not oversell it, that you think about this triangle, right? And think about where x and y on this triangle, where r and theta on this triangle, and trig comes to mind, right? And you can persuade yourself pretty quickly, I think, that this is the formula for how you compute x and y from r and theta. Okay, now, I am going to point out, and I think this has to get said, generally not a good idea to think about trig in terms of triangles. Instead, I do encourage you also to think about trig in terms of the unit circle. Right? The problem with triangles is they're restricted to only certain angles. There's no such thing as a triangle where one of the angles is 7 pi. It's not a thing. Right? So, but on the unit circle, you can absolutely just go around 7 pi radians. Right? That's no problem. Okay. How we doing? Yeah.
Scroll down just a little bit.
Mm-hmm. Yeah. Just keep in mind all of this is on the notes that you can download at your leisure. Okay, so now here's the trouble with this section. The trouble with this section is, again, there's a lot of little details, right? And ultimately, polar coordinates is not It's not one of those topics that oh my gosh, that's going to be a tough one for students to learn. We really need to dedicate a lot of time to that one. It doesn't really rise to that level, right? So a lot of this is going to be, y'all can read this on your own. As you've noticed, I'm sure when I have that in the notes, what that usually comes down to is I'm just going to go through it really quickly, right? Because I do like to hit sort of the highlights. So here, for the lack of uniqueness, let me just point out that if you think, again, I think this is very handy to think of polar coordinates as a function. The idea of adding 2 pi to the angle, if you think about it, adding 2 pi to the angle just takes you around a full turn, and check it out, you go back exactly to the same point you had been at. So that's nice. Here's another lack of uniqueness. Notice if you add pi to the angle, that'll take you around a half turn. But then if you also negate the r coordinate, then that will take you the other direction. And again, you get back to exactly the same point you had been at. Right? So there's in some sense 2 different ways to produce infinitely many different polar coordinates for any single point. Is that satisfying? Everybody buy it? Okay. Details, make sure to read. This is probably me being maybe just a little OCD, but I think this is really important to point out that if you're vague about what coordinate system you're talking about, you can create confusion. So, for example, if I write down 2 pi over 6 and ask you where's that point, honestly, that pi over 6 kind of looks like an angle. I think maybe you're telling me the polar coordinates. If you're telling me the polar coordinates, then that would suggest this point. But here's the thing. Pi over 6 is a real number. It could absolutely be a y-coordinate. There is no law that says convenient multiples of pi must always be viewed as being angles. Not at all. Right? So this could be the xy coordinates, in which case we're talking about that. So which is it? Right? What has been written down here that I have, boxed in this dark blue, is ambiguous. Not clear what that is. So heads up on this. If you see in some other work that you did not produce yourself, something like that, your ears should perk up. You should look for some sign or indication of, well, wait a minute, which is it? Notice how easy it is to do. You can just say r comma theta equals, and now ambiguity removed. No one's unsure what you're talking about there. Okay. And then so likewise, you should clarify if it isn't already clear from where it came from or something. But look how easy it is to do, and why not be clear? Okay. This next one, this is another really important one. A lot of students have been told some little fibs in high school algebra classes. And in particular, one of the fibs that we're told is that this equation means the same thing as this equation. And they do not mean the same thing. I want to make extra sure that everybody walks away from today's lecture clear that these are different. And here's the difference. This top equation that I wrote in purple says R is positive. That symbol right there, the square root symbol, that means positive. It does not mean whichever number you choose or is convenient for your purposes. Right? That also has the feature that when you square it, gives you what it's supposed to. That's not what that symbol means. It means positive. And so if you want to represent, for example, both of the real square roots of some number, that's why they actually write plus minus. Because you have to say that. Otherwise, you're talking about the positive one. Does that make sense to everybody? Okay, so this top equation that I've written down says R has to be positive. Again, no it does not. Notice this bottom equation says no such thing. In this bottom equation, R could be either positive or negative. And no indication. Okay, so this bottom equation is true. This top equation, not necessarily true. In other words, you can't trust it. In other words, bad idea, don't write it down. Is everybody on board? Okay. Likewise, up here, you're going to feel this urge to solve for theta, and you're going to write it down as arctan of y over x. I'm ignoring when x equals 0. Let's not worry about that. Again, not true. Arctan means specifically a certain range of values, certain range of angles. Theta is under no obligation to be in that range, right? So again, it's just not true. And I encourage you not to write down stuff that's not true. Does that make sense? It's kind of opposed to what we're interested in here. Yeah. Okay, so resist that temptation, and notice how it will give you straight up wrong answers, right? So let's look at, let's see here, this point, -1, -1. There you go. Right, x, y, -1, -1, there you go. And here's the thing, if you were to use those purple formulas up there, those purple formulas would suggest, well, I guess R must be square root of 2, and I guess theta must be pi over 4, and that would put you right there, which is wrong. There's no need to candy coat it. It's wrong. Does that make sense? So this is just an example, right? This is not really why I don't like these formulas. I don't like these formulas because they're false, right? But this is, if you're not persuaded by that part, this is a landmine you can step on if you make the mistake of trusting those purple formulas. Yes?
If you didn't do it that way and you did it the R squared, you had the plus or minus,
yeah.
You would get both points.
Well, what it would do is it would tell you, you would get a bunch of candidates, right? So knowing that R must be one of these two values, knowing that theta must be one of these, however many values, doesn't mean that they'll all work, right? And so all it means is you're not done yet, and you have to decide. In other words, further work that must be done to determine which of these other points is the right one. So, for example, I guess pi over 4 is one of the possible angles. Well, pi over 4 would have me going that way, and now I have to think to myself, what values of R can I select to get to the point that I want? Can I use this one? And you got to think about it. Right? I encourage you to think about it geometrically, right? And I look at that square root of 2, and I look at the theta that I've already chosen, and I see that would put me here. I see that that's wrong. And so I don't choose that. Right? So you can't take that one, and then you notice that minus square root of 2 gets you exactly where you should be. Does that make sense?
Yes, but how would you know where you're exactly meant to be without being told, explicitly?
You are told. You're told that x, y is -1, -1, and you know where that is.
Okay.
Does that make sense?
Yes.
Yeah. Everybody happy with that? Yeah. Okay. So here's another implicit bit of nonsense that gets told in a lot of high schools. I don't know about yours necessarily, but certainly in my high school, I was told that you plug into the formula and it gives you the answer. This is not true, right? Very often it gives you options that you have to kind of choose from, or it breaks the problem down to various, sub-problems that you can think about in some other way, right? But you can't always just trust that, you just plug the formula and it'll work. Okay. All right. Okay. Again, more stuff that doesn't rise to the level. These two examples here show how you can take, in some cases, polar equations and how you can convert those into rectangular equations. And in both cases, there's a little trick to be played. And in both cases, not very much, but a little bit of algebra. Here we're taking advantage of the fact that r squared is x squared plus y squared. And you see how I cleverly arranged for that to be useful. and thus got to my answer. And in this case, you can see that I was taking advantage of the fact that tan theta is y over x, right? And again, I cleverly arranged in doing some algebra to give that the opportunity to fit, right, and to be part of my process. And so, a couple little cute examples. This next one is a little bit more challenging, so I want to talk through at least part of this one. Such games are not going to work for this one, right? That I'm aware of. And I think you can probably persuade yourself that, you could, let me say it this way, you can try and, you'll probably fail too, right? I don't know how to just write down algebra like the above examples and plot this, right? So sometimes when things get weird, you have to really just kind of, in some sense, point plot. Right? So here's the way this can break down. I'm going to consider different ranges of angles. So we're going to start by going from 0 to pi over 2. Specifically, theta is 0 to pi over 2, and of course that's these angles sort of here. Okay. Don't make the mistake of thinking of this as the angle. There are two angles that participate in this example. Theta is the polar angle. 2 theta is the argument of the trig function that we're going to be plugging into. And 2 theta is not to be conflated with theta, right? They're clearly different. So even though theta goes from 0 to pi over 2, 2 theta goes from 0 to pi. And if I ask, as we go from 0 to pi, what happens to r? In other words, as my argument goes from 0 to pi, what does sine of that argument do? Well, r starts at 0, and then it gets bigger, it makes its way up to 1, and then it starts going back down and makes its way back down to 0. Right? So the punchline here is that as theta ranges over these directions, right, for those values of theta, r is going to start at 0, increase to 1, and then make its way back down to 0. And when you just start going one at a time and start plotting in these directions, as those thetas do as we described, and plotting how these r's do as we just talked through, this is the resulting picture you get. Does everybody see that? All right, so it's a good one. By the way, very often, what you're going to find is that, stuff that I say in class, you're going to be sort of at, okay, I think I sort of 60% get that, right? Fine, no problem. After class, spend a little bit more time with it. All you need, right? Let it sink in, get yourself up to 100%. Get yourself up to 85 or 90%, and then come to office hours for the remaining 15, or whatever you got to do, right? But anyway, sometimes you will need to revisit and let things soak in. Right? I'm going to encourage y'all to think through the remaining 4 quadrants. Right? So I drew the quadrant 2. Quadrant 2 takes you down here because r becomes negative. Right? And then think through quadrant 3 and quadrant 4, and you end up with kind of a 4-leaf clover looking kind of thing. Okay. Lastly, there are some examples, just more examples. There was a different trick in this first example. How did I turn r into r squared? I didn't do it by squaring both sides of the equation like we did previously. I did it by multiplying by r on both sides of the equation. And the reason why is cosine squared, I don't know what to do with. But r cosine theta, I totally know what to do with. So this is just another clever trick, right? I figure, if you've seen most of the tricks, then when those tricks are needed, hopefully that'll, stimulate the thought. Okay. All right. Oh, by the way, also notice here I did this thing where I added a fourth to both sides of the equation. This is called completing the square. Do y'all have flashback memories to, I don't know what they used to call it Algebra 2 when I was in school. So anyway, in Algebra 2 or whatever, this method gets noted, and it's what allows you to rewrite that as a perfect square, which is what allows you to recognize this as being a circle. Right? So anyway, make sure you're good with that algebra. It goes way back, middle of high school or something. So if you're not good with completing the square, good news. I'm sure there's a million resources online to get good at it. You're also, as always, welcome to come talk to me in office hours. Happy to tell you my take on that. Okay. And I think this one's pretty straightforward here. I'm just going to point out really quickly. Notice sometimes the algebra can be convenient to square that out first. Don't go plugging in the formulas yet. You square that out first, and then notice you can almost for free just recopy that. And that saves me, an appreciated amount of trig inconvenience that I don't really want to have to deal with. Okay. All right. Okay, moving along. So, cylindrical coordinates. It's a different coordinate system. This is for 3 dimensions. You'll notice polar coordinates was for 2 dimensions. Now we're in 3 dimensions. A lot of people refer to cylindrical coordinates as being polar coordinates in space. I think it's a reasonable thing to call it. I do believe that cylindrical coordinates is fewer syllables. I think it's an easier thing to call it. It also has the nice feature that it keeps it distinct. Right? I don't like to blur things that aren't the same if we don't have a compelling reason to do that. Right? And here I just don't see a compelling reason. So I prefer to call this cylindrical coordinates. I'm not super uptight about it though. So the big idea is that, it's literally r and theta as far as x and y are concerned. And you'll recognize down here that the r and the theta are interpreted the same way. You're going to recognize all of these equations here, exactly the same formulas that we wrote down in for polar coordinates. The only difference is that cylindrical coordinates has this third coordinate z, which relates to rectangular coordinates by being the third coordinate z. Very little happened here, right? Just don't forget your z, arguably, is what cylindrical coordinates is. Does that make sense to everybody? So that's the good news about it. Not a tremendous amount to say about this. I mean, I do like to point out that this very simple formula you can plug into there and recognize will give you a cylinder. Right? If you want to see it as, from the rectangular formula for a cylinder, that's how you would get that. Or you can just think to yourself, hey, you know what? What are all of the points that are a set fixed distance c away from the z-axis? And not hard to persuade yourself that's a cylinder. Okay. Here's another conversion. Here we have a rectangular equation for a sphere. Okay. And notice, I can just do like so. And check it out, lo and behold, now I have an equation that is no longer in rectangular coordinates. This is now an equation in cylindrical coordinates, otherwise known as a cylindrical equation for that same sphere. So, kind of cool. Is everybody on board? Is everybody happy? All right. This next one's a little tricky. This next one absolutely does deserve a little bit of discussion. A lot of people will get this wrong. So z equals kr. What are we going to do about this? Well, a lot of people will think, okay, well, r is the distance from the z-axis. So let's see here. Okay, so you go up by however far you are away from the z-axis. And here's the problem. If you take that point of view, you will only notice sort of the top part of the cone. And the mistake, you probably caught me. I did it on purpose, by the way, in my defense. But I interpreted r as being a distance. No, it's not. R is a coordinate. It's not a distance. R is allowed to be negative. There's no problem with R being negative. You cannot just assume R is going to be positive. Okay? So if R could be negative, then so can Z. I'm presuming K is positive, or whatever. Okay, so there's that. Okay, so what is this thing anyway? Well, here's a really clever idea. I'm a big fan of this idea. If you fix a value of theta, right? Let's momentarily remind ourselves, what is theta? You know, theta is this angle right here. And if you ask, well, what are all of the points that have that fixed single value of theta? Well, it's going to be what I like to call a half plane. And by the way, it could be lots of different half planes depending on which theta you pick. Maybe it's this one, right? Maybe it's this one. Maybe it's that one. Maybe it's that one. Lots of different half planes depending on the theta, right? And I like to think of this as kind of like a door that's swinging around the z-axis. And if you think about it, if it's swinging around the x-axis, that means the hinges of the door will be on the z-axis. And so this is the little terminology I like to go with. This is a half plane hinged on the z-axis. Okay. So, okay, well, what would happen if I insist on a fixed value of theta? How does that affect the equation? And of course, the answer is not a bit. There are no thetas in that equation. The equation doesn't change at all if you insist on a particular value of theta or a different value of theta or whatever. Pick any value of theta you want. You're always going to have the same equation remaining. Right? So the punchline there is that means that all of the cross sections, all of the theta cross sections of this thing, all of those theta cross sections look exactly the same. Does that make sense? And so, okay, well, pick some value of theta. Looking in any one of these cross sections, I mean, right? It's not hard to see if Z is a multiple of R. You're just going to get a straight line. And so what we conclude then is that our surface, whatever this surface is, whatever this equation represents, well, all the cross sections look like this. All the cross sections are lines like so. No matter how you go around, right? So said differently, you can take one of those lines and you can rotate that line around the z-axis and it produces the surface that we're interested in. I think this is a really nice trick, really valuable idea. So please always be on the lookout for this. When you see a cylindrical equation where there's no thetas in the equation, rotationally symmetric around the z-axis, and furthermore, you can produce it by rotating any cross-section of it. Everybody happy? Okay, so neat trick. Okay. Oh, yeah, by the way, just a heads up, confusion of variables is this kind of triviality, but it's a triviality that can really create problems. So, sorry to have to bore you with something silly like this, but very often we like to use R to represent given constants. Like, oh, I have a sphere given to me, and it's a sphere of radius R. Very often it's an easy choice, right? You can't do that when you're going to be using cylindrical coordinates, because R is a variable. Right? So, for example, it'd be like okay, I have a box, and the height of the box I'm going to call it X. You probably can't. I mean, the X has already been spoken for. X is a coordinate, right? You can't just go around arbitrarily saying the width of the box is X. No, X is a variable. And you got to name your width something else. Everybody see what I'm saying? Okay, so good news. You could use capital R. Right? You could use R naught, a little subscript, or something like that. Just anything other than lowercase r. Okay, let's talk about spherical coordinates. Also, very often referred to as polar coordinates in space. I think that's a bad idea. I'm pretty opposed to calling this polar coordinates in space. Because we already agreed that cylindrical coordinates pretty reasonably could be called polar coordinates in space. And now again, you can't use the same term to refer to two importantly different things. Right? So, this has less in common with polar coordinates. So I think this is the least compelling candidate for that title of polar coordinates in space. So again, bad choice. All right, so what is it and how should I think about spherical coordinates? Here's my take. Spherical coordinates are these three values. By the way, in case your Greek is not up to speed, that's theta. I think everybody knows that one, right? This is called phi. It's spelled like this and pronounced like that. Right? And this is called rho. Again, spelled like that and pronounced like that. Please do be careful about this one. That is not a P. You can't write it with a P. P is a different letter of the alpha of a different alphabet, right? And it very well might mean something different. And if someone reading your work sees a P, they will not just get that you meant rho. Right? So if you're not already proficient and accustomed to making this new letter called rho, I know it seems silly to have to do this, but you might have to sit down with a clean sheet of paper and, make yourself a few dozen rows and decide, are you gonna be a counterclockwise, inside out person or a clockwise outside in kind of parade? Whatever. I have no position on that. Right? Suit yourselves. Okay, so here's how I like to think about spherical coordinates. I like to start with theta. We've already talked about theta. This angle theta defines a half plane hinged on the z-axis. Boom. Okay, there we go. That's what theta is. Okay, next, what is phi? Phi is an angle like so. It's an angle measured off of the z-axis. But very importantly, which direction off of the z-axis do you go when you're, increasing phi? If you're at the vertical, right, phi equals 0, and somebody says, hey, let's start increasing phi, and so you're going to tilt away from the z-axis, which way? And very importantly, toward the theta half plane. Right, so you don't have to view it this way, but I think a very reasonable take on this is think of you can't even really talk about phi until you've already settled what theta is. Because I can't, talk about, well, how far do I go off of the z-axis if I don't know in which direction off of the z-axis do you mean for me to go? Does that make sense? Okay. All right, now you'll notice that between the two of these, between both of these angles, that defines a direction. And again, once you have a direction, you can talk about, air quotes, apologies, asterisk, how far to go in that direction. And, so positive means go in that direction and negative means go the opposite of that direction. Does that make sense? Okay, so what are our conversion formulas? Let's see, I guess this doesn't quite fit, so let me do like so to get everything to fit here. Pretty much everything you need to identify the conversion formulas comes from this triangle right here. If you think about the trig of this triangle and what we already know about cylindrical coordinates, right? So trig plus known formulas allows you to conclude these conversion formulas. Now, for for your possible convenience, right? As long as you remember that that triangle is actually there as I have it drawn, you can sort of redraw that triangle where you're looking kind of more straight on at it, right? And then make the observation that that angle phi, being that angle, is also that angle. And now it's arguably a little bit easier to look at this triangle and see, remind yourself of the trig, you can do the trig from there. So, if that's useful, cool. By the way, another really useful point of view on this, notice that this side of the triangle is literally R from cylindrical coordinates. So, we already know that that's R. And by the way, we also already know that X and Y are R cosine theta and R sine theta, right? So seeing that, seeing that R is rho sine phi from the trig of that triangle makes these first two equations pretty easy to motivate. That's just plug in this new observation about R into our existing cylindrical conversion formula. Okay, and then of course you notice that, let's see, color choices. This is Z, and again, a little bit of trig, and now we're done. Okay, so for your consideration, it's probably a good idea strategically, just from a how to do well in this course point of view. Yeah, you should probably go ahead and memorize these conversion formulas. That said, I'm going to note for the record, I think it's fair to say that I've never done that in my life. Kind of like with that determinant formula, right? I have a different way to get these formulas when I need them. And that is, I think about this triangle. Every time I need these formulas, I think about that triangle and I reproduce them. Because, honest to God, I trust my trig better than I trust my memory. Right? And so I think there's something to be said for that, right? Now in the short term, right, if this is going to be on the test and, what do you do? Well, night before, if you want to drill these formulas so that you have them boom, right at the tip of your tongue, and you want to save yourself the 30 seconds it would take to sort of write this down and think it through. Sure, absolutely. It's probably a good idea, and I encourage you to do that. But 15 years from now, you're not going to remember that, right? But 15 years from now, I hope you do remember that one triangle and just a little trig, right? It's really not that hard to rederive them. Okay, so again, a couple of easy starter examples. Easy relationship between x, y, z, and rho, kind of a Pythagorean relationship. Not hard to see where that comes from. Make sure you can argue. Make sure you can prove that. Right? Think about the geometry of the picture and persuade yourself that that's true. And of course, if you plug that in as a constant, then this turns into, good enough. Turns into a sphere centered at the origin. So that's where the name spherical coordinates comes from. Okay. This is a really good exercise. Y'all remember we talked about the lack of uniqueness of these new coordinate systems, and just like with polar, spherical coordinates are not unique. In some sense, there's kind of two ways to represent a point in polar coordinates, because in some sense, with that angle theta, you can either be going in exactly the right direction, or you could be going exactly the wrong direction and have to use a negative value wrong. Right? So there's plus 2 pi, any number of 2 pi's, that's kind of boring. So there's basically two different ways to do it in polar coordinates. Spherical coordinates has two different angles, each of which, for which you have two options. And so in fact, there are 4, importantly different ways to represent any point in spherical coordinates. And it is a confusing, disorienting, but ultimately, good good little bit of mathematical weightlifting. It'll make you a better mathematician, right? You'll have a better sense of the geometry of spherical coordinates if you think through, go through the confusing, wait a second, which way, go through all those details with an example like this. It really helps. So let's walk through this one. Now again, I'm going to give you a lot to think about here. So you're probably going to have to give yourself a little time to digest conveniently with the recordings. By the way, if you need to hear some of this a second time, right, no problem. Make a little note in your lecture notes and come back and listen to the recording at a later time, right? No problem. You can listen to it as many times as you want, right? Okay, so that point, which I've put there, a little bit of geometry, right? You see some triangles, right triangles. You remember all your trig and all that stuff, and you can persuade yourself what these angles are there and there. And so that's just geometry, again, exercise for y'all to do. So that said, how do I interpret from this some spherical coordinates? Well, I will start by saying, well, I see my point is in that half plane. I'm going to choose the value theta to be pi over 3. Okay. And then for that theta, I could say, okay, well, there's my positive direction for phi, and in that direction, I'd want to go pi over 4. In that direction, that gets me going in the correct direction altogether, and in that correct direction, I go that distance, which again, work out the geometry. That's all totally doable. Okay, so that's kind of the easy option, right? First easy option. Here's another option. Let's stick with pi over 3. Right, so same theta choice. But check this out. I could go backwards. I could rotate away from the half plane by choosing a negative value of phi. Right? Positive value of phi goes toward the theta half plane. Negative value, therefore, goes opposite. Now, this is where the geometry is going to get a little challenging, and you just have to contemplate and see it, right? It's confusing, but in that negative direction, I could go however far as necessary to get me going the exact wrong way, and in that exact wrong direction, I would need to go a negative row, but that would still, in fact, get me to this same point. Yep.
How do you find, you just solved the algebra?
The geometry. Yeah, so you remember we were talking about you can do the geometry and the trig of the givens, and so this down here is this is a 45, 45, 90 triangle. Let's see, is that there? No, I'm sorry, I have my numbers wrong. This is a 30, 60, 90 triangle.
But how would you just know that?
Because so this is 1, this is the square root of 3, and that's a right triangle, so that's a 2, and that's a pat known thing. Does that make sense? Yeah. Yeah, okay, so what is this angle here? Well, you gotta be careful about this. That is sort of opposite, if you will, of this angle. This angle we've already decided is pi over 4. So at least in terms of how big this angle is, the magnitude of this angle is 3 pi over 4. But wait a minute, it's a negative value of phi. So it's negative 3 pi over 4. Or, if you prefer, alternative, different way to think about it, we've already agreed that, we've already agreed that is pi over 4. And I could take that pi over 4 and then say, you know what, I'm just going to subtract pi from that pi over 4. Half turn. Right? That half turn gets you going the exact opposite direction. And subtracting pi from pi over 4 gives you the same minus 3 pi over 4. Yeah.
Could you also like represent that p with 2 more angles, like positive pi
Yep.
pi over 4?
You can represent it with infinitely many more angles. Absolutely. Yeah, so this is just one way to think about it. Yeah. So another option, you could add pi to pi over 4. So yeah, 5 pi over 4, totally fine. You can add as many further additional 2 pi's however much you want. Okay. All right. Okay, so now I'm going to get you started on the next 2, but I think this is a really good exercise. Everyone should do this for themselves. Plus, we're almost out of time here. That clock is it's disappointingly accurate. So your other option is to think about theta going the other way. Let's choose that value of theta. 4 pi over 3. That has you going, that's sort of, that's the half plane opposite of the point that we have, right? And now think about, well, what are the different ways to get to this point? And one way to do it would be to use a negative value of phi. That's now, this direction is now a negative value of phi because theta goes that way. Okay? And then, of course, you can add pi to get going in the opposite direction. And then think about what rho has got to do. Good details for y'all to work out on your own. We'll draw the line right here. Y'all have a great weekend. See you on Monday.